atmosphere here is always so stimulating. It's really a great pleasure to be here. So today I would like to talk about this joint work with a student of mine, McKee, and my colleague from Gothenburg, Turowska. It's about some sister algebra, let's say, versions of rather classical results. If you replace the sister algebra by the scalars complex field, you get results that were quite well known for a number of years. So that's the general sort of, from a very general perspective, what I'm going to talk about. So I will introduce all these things, of course, Schur multipliers and the related notion of Schur multipliers. So first of all, what are Schur multipliers? Or the measurable version of Schur multipliers goes like that. You start with two standard measure spaces. So it measures mu and mu. And of course it is very well known that if you have an L2 function on product measure space, it is a kernel of an integral operator, which is a Hilbert-Schmidt operator. As the usual formula defining an integral operator. So it acts from L2 of x into L2 of y. Now if you have another function on the product space, say essentially bounded function, measurable function, you can consider the pointwise product of a kernel of an integral operator, a Hilbert-Schmidt operator, with your given function. Surely when you consider this mapping sending k to phi k, it is a bounded map in the L2 norm, because I started with a function phi that was essentially bounded. However, the space of all Hilbert-Schmidt operators, apart from the Hilbert-Schmidt norm, which corresponds to the L2 norm of the function, of the kernel, the integral kernel, can be, of course, equipped with other norms of interest, and most of all, the operator norm. So when you consider this map, sending k to phi k, equipping the corresponding functions with the operator norm, we do not always get a bounded operator. And that's the point. You single out those functions for which this mapping defines a bounded transformation with respect to the operator norm, and you call those Schur multipliers. So this is the definition of Schur multipliers. Now, very nicely, it turns out that if this map, well, first of all, of course, if this map is bounded, so if you have a this is the map I consider. This is a map from of course C2, Hilbert-Schmidt operators, which is bounded in the operator norm. Then, of course, it will extend to the compact operators. The bounded map on the compact operators, surely so. But very nicely, in this case, the corresponding map here will be not just bounded, it will be completely bounded. So, should I remind the basics of complete boundedness? Completely bounded maps. What is the difference? So, maybe quickly, yeah. So, basically, if you have we are interested on maps, linear maps on operators, on spaces of operators here to start, right? So say you have the space of all bounded linear operators on some Hilbert space, and you have a transformer, or otherwise speaking, it's just a linear map on BOH. Of course, BOH comes with its own operator norm, so you can single out the class of bounded maps here. But in addition to those, actually, there is substantial interest in a smaller class of maps, which are not only bounded, but satisfy a stronger condition of boundedness. What is that condition? Well, it goes like that. Let me consider the cuboid matrices with entries in BOH, entries operators. Right. So this can be identified in a canonical way with the space of all bounded operators on the direct sum of H with itself. So, that's the usual way. Matrices with scalar entries. And now you can consider, along with your map, let's call it phi, you can consider the amplification of this map, if you want. Okay. One way to define it. Okay, you just apply your map phi entry-wise to your to matrix to get another map on this space here. And now, if your first map is bounded, it is quite easy to see that this map will be bounded as well. However, its norm may increase. It doesn't need to stay the same. Its norm is at least equal to the norm of the original map, but perhaps it can increase a little bit. And now you're doing this same kind of thing, but for all sizes of matrices. At each level n, you have a corresponding norm. And this originally bounded map, phi n will be bounded. These norms in general will increase, and you are asking what's happening when you take the supremum over all those n's. And if it happens that the supremum is finite, then by definition, you call the map completely bounded CP. For sure. Very well. So these are the completely bounded maps. As I said, in general, norms of phi n may increase. In general, they are not. The supremum is not finite. In general, easy example to see that. However, very nicely, when you have a Schur multiplier, it turns out that these norms, the sequence of norms, actually doesn't increase at all. It stays the same as the first level. So the CP norm of such a map will be equal to the original norm of the map. Right. So that's a nice result. It is true slightly more generally, but the settings in which it's known to be true are not very far from such a situation, from being a Schur multiplier. At least the settings that are known, they do not have an increase. I'm not aware of any characterizations of precisely when the norm doesn't increase, but the known results are not very far from such a situation. This fact is based basically on the result of Herrera-Smith's. Very well, so then these are Schur multipliers. Which functions are Schur multipliers? Not all functions are Schur multipliers. That's not difficult to see. Some of them are. So this is a characterization of the functions that are Schur multipliers. Well, for example, imagine where you have a function that factorizes. So your phi is a of x times b of y. In that case, the corresponding map that you're considering will be just like that. Will be just multiplying operator that multiplies on the left and on the right by some operators A and B, which start. This will be an operator acting on b of L2 of x. More precisely, it will be a multiplication operator by an essentially bounded function on x. And so basically, if you have a function here f, and you can consider the operator, let's call it mf, which is extending a function c to x. B is a similar thing, but for y. So, of course, if you have such a situation, then of course this is bounded, this is completely bounded, and of course, if you have sums of those, finite sums of those, they will of course satisfy the boundedness condition again. And this result, this characterization basically says that the general case is not very far from that. Finite sums are not enough, but infinite sums suffice. And the conditions that give you these infinite sums are just natural conditions, natural convergence conditions, which will ensure that this series here that you see on the right-hand side is convergent. Now, the situation where we have counting measures on the spaces x and y is also of interest. In fact, of interest for computation of norms is even the case where we have finite measure spaces. You have just matrices. In this case, what we have is just pointwise, entry-wise multiplication when made. So the functions, the operators that we are talking about are just entry-wise multiplication by a fixed matrix. So as I said, even this case is not uninteresting when you have here counting measure, and it was first obtained by Grothendieck in his functional analysis days in the 50s as part of his resume. Now, how does this relate to groups? The philosophy that one follows here is that harmonic analysis can be viewed as theory on one variable, because you have groups. So once you have group, what you're interested in, okay, let's study functions on groups. So they depend on one variable, let's say. So operator theory, on the other hand, is a theory that is a two-variable theory. Why? Well, because, for example, Hilbert-Schmidt operators that I defined in the beginning, they have integral kernels which depend on two variables. Matrices, they're indexed by two rows and columns, by two variables. Okay. So operator theory being a theory of two-variable theory, harmonic analysis being a one-variable theory, there is a way to embed harmonic analysis into operator theory and consider harmonic analytic functions as part of operator theoretic notions and concepts. So this is the general sort of picture, general philosophy one can follow. So more concretely, if you start with a locally compact group, discrete groups are also of interest. Lambda, let's note like lambda, the usual left regular representation of the group, then it lifts to a representation, left regular representation of the L1 convolution algebra of the group. Acts by convolution like that. And let's note by LG, as usual, the Fourier algebra of G. So what is the Fourier algebra of G? In a case the group is abelian, then you take L1 of the dual group, and then you take Fourier transforms, and you obtain the Fourier algebra. This is the space of all the algebra Fourier transforms of L1 functions. So that's the Fourier algebra. Now, if the group is not commutative, then you need to do a little bit more. Design a right sort of generalization of this object. And that was done by Aymar in the 60s, and he defined the Fourier algebra of a general, non-commutative group. In the following way. So these are functions. So the nice thing about it, it's an algebra of functions on G. G is a locally compact group. We have continuous functions on G. So A of G is a sub-algebra of all continuous functions vanishing in infinity on G. Which algebra precisely? It is the algebra arising in that way, functions arising in that way. You fix two vectors xi and eta from L to G, and you shift xi by a certain phase S, and then you take a look at the inner product. What's happening with the inner product? Lambda S xi with eta. How does it depend on S? This is your function, U of S, which is a typical element of the Fourier algebra. Of course, you would have noticed immediately that indeed this generalizes the commutative situation, because if you have an L1 function, factorize it as a product of 12 functions, and then take the Fourier transform. This is what you will get. This is simply a different way to write the convolution of xi and a little bit of a twist of eta. Very well. So now operator algebraic objects associated with groups. So this was the Aymar's philosophy. He introduced functional analytic methods in the study of groups, of non-commutative groups. He attached sister algebras to a group, von Neumann algebras to a group. As I said, he defined his Fourier algebra, which is more of a harmonic analytic inspiration. What is the sister algebra? Well, for the sister algebra, for example, you just take the image of L1 of G through this left regular representation. That's a certain star algebra, sub-algebra of B of L2 of G, and you close it as the sister algebra of the group, the reduced sister algebra of the group. We can talk about the von Neumann algebra of the group just by taking weak closures of this sister algebra, and these are nice, actually perhaps not so nice, rather difficult from operator algebraic point of view, operator algebras, because basic questions about those are still unresolved. So questions about, for example, the von Neumann algebra on some very simple, from group theoretic point of view, the simplest groups are free groups, perhaps. So if you consider the von Neumann algebra of free groups, it's very sort of open questions, basic open questions of, for example, if you have different number of generators in free groups, is the von Neumann algebra the same? That's one of the famous open questions in the area. So these are from operator algebraic point of view, these are not the easiest algebras to handle in a sense. While from group theoretic perspective, as I said, for example, free groups are the easiest from group theoretic perspective. in any case, once we have these objects, what can be seen, and this is what Emmer did, he showed that the dual Banach space of the Fourier algebra is precisely equal to the fundamental algebra of G. What is the duality here? Not surprisingly, if you have an operator, now this is an operator acting on L2, U is a function coming in that way from two vectors C and eta. Well, we just have the corresponding vector functional, tc paired with eta. In that way, you have a duality between A of G and the operators in the fundamental algebra of G. It's a consequence of functionals on the fundamental algebra of G. Normal functionals turn out to be vector functionals. Now, what is a Hertz-Schur multiplier? So we have, if you have a function u on G, which multiplies A of G into itself, in the sense that it sends the map sending V to the pointwise product UV has range again in A of G. Not all functions will be such. That's called a multiplier of A of G, or bounded multiplier. It will be automatically bounded with respect to the canonical norm of A of G as a pre-dual of the fundamental algebra of G, for example. When this map is not only bounded, but completely bounded, we are talking about completely bounded multipliers of A of G, or also called Hertz-Schur multipliers. What does it mean that this map is completely bounded? There is perhaps an easier way to talk about it is the following. Instead of, both ways are fruitful in some way or another, but if you have this function on G, then you can consider the map on generators of the fundamental algebra of G, sending lambda t, remember this is the left regular unitary, to just a multiple of lambda t. And so this for all t in your group. And you're asking, you're collecting together those functions for which this map extends to a completely bounded map on the fundamental algebra. This gives rise to a map on the fundamental algebra of G to itself. Those functions for which this map here extends to a completely bounded map on the fundamental algebra of G are called Hertz-Schur multipliers. All right. Now, this general sort of broad picture that I was trying to paint, that harmonic analysis being one variable theory and operator theory being two variable theory. How is it reflected here? Well, given a function on one variable, on G, you can define a function on two variables just using the fact that you have defined your domain is group times a group, just by multiplying the two variables together inside the argument of the function. And now there is a result that characterizes, so it has a long history. I haven't given the full sort of history here because this result has a long list of names attached to it. What I have done is I have given the names of the authors that this precise statement is encountered. But as I said, the result has a very long list of names associated to it. This interplay between Hertz-Schur and Schur multipliers. What we know is that a function u is a Hertz-Schur multiplier precisely when this new function that I formed like that, I called n of u, is a Schur multiplier. And remember, Schur multiplier means that it has this nice representation, almost factoring, infinitely sort of approximate factorization. Very well. So this result has been useful in many contexts in operator algebra theory. So I will talk about it here exactly. So motivation. First of all, as I said, it's generalization of ng-wise product of matrices. And of course you would ask me, so why care about ng-wise product of matrices? One reason to care, for example, is that it's of importance in a number of questions, especially in applications. If you have a matrix that not all entries are known, you want to replace the unknown entries with zeros. But you still want to have control of the norm of the matrix. Well, what you're doing here is exactly Schur multiplying by a 0-1 function, your matrix. Yeah? And what is the norm of such thing? Of course, if you have finite matrices, the norm is always finite. The question is, what is the norm? Does it grow indefinitely as the size of the matrix increases, for example? One well-known result is that if you take the so-called triangular truncation, where you replace the entries of the matrices below the diagonal with zeros and keep everything else the same, this is unbounded if you go to infinite dimensions. Yeah? That's a Schur multiplier. Well, it is not Schur multiplier because it's not bounded. It is an entry-y product. So it's a Schur multiplication. It's an entry-y product with a function. So that's one motivation. I mentioned operator algebra theory. So Schur multipliers were introduced by Haagerup and Canniere. So they had this idea of using these maps in order to study approximation properties of operator algebras. There is a long, of course, long history of problems about approximation, finite dimensional approximations of infinite-dimensional objects, going back again to Prof with the metric approximation property in Banach spaces. When people studied operator algebras, they saw that it's useful if your operator algebras can be somehow finite dimensionally approximated again. And there is a large set of approximation properties. I will show you some of them towards the end of the talk, which are studied in operator algebra theory of interest there. And Haagerup and his collaborators studied approximation properties. So I have to mention Canniere, Cowling, and other collaborators studied approximation properties of operator algebras, group operator algebras like the sister algebras and the fundamental algebra that I mentioned before, using these types of maps. For example, the first example of a nuclear algebra that doesn't satisfy the block-and-Dix approximation property was designed by Haagerup exactly using this kind of maps. Right. So now, what is our contribution to this? So as I said, roughly speaking, we replace the scalars with the sister algebra. And you would ask me why we do that. And one answer is already contained in the previous slide. If you want to study approximation properties of cross products, operator algebras that are cross products, this is where you are led to inevitably. Well, at least if you want to use somehow the already generated lore about approximation properties. So the definition, you start now with a function, L2 function on your measure spaces, but not C valued, scalar valued, but A valued, where A is a sister algebra, a completely representative sister algebra. You can design very easily a corresponding map which resembles the integral operator, resembles the Hilbert-Schmidt operator that I defined before. The only difference is now that it will be acting on, not on L2 of x, it will be acting on H-valued L2 of x, with values in the Hilbert space H. H is the Hilbert space where A acts on. This formula is, so over here, Xi of x lives in H, Ky of yx lives in A acts on H, so you can act with K of y, comma x on Xi of x. So you obtain a vector in H. You integrate. That's a well-defined vector, and it's a bounded operator. It satisfies a nice property that it's zero only when k is zero. These are just trivial things one sees immediately, and then these operators, the operators of this form, are dense now not in the compact operators as before, but in the minimal tensor product of the compact operators with the sister algebra A. And now, what are the Schur multipliers in that case? So here, what we have are functions phi defined on C cross Y. The values will not be scalar, but they will be valued in the completely bounded maps on A. You can think about here that I do not consider from A to B of H if you want, just on A, for example. What is the corresponding version of pointwise multiplication of the two functions? Well, here phi has values in CB maps on A. K has values in A, so you can just apply a map phi on K entry-wise. That's the natural thing to do. Again, it is certainly a bounded map in the L2 norm, and whenever it is a completely bounded map in the corresponding operator norm, then you declare it a Schur multiplier precisely the way we did before. Of course, here you need to be careful because not all bounded are completely bounded here. If you have an arbitrary sister algebra, it's not true that all bounded will be completely bounded. So we are singling out completely bounded, simply, well, not simply, but one reason is really that, first of all, they are mappings of most interest, and then there are tools developed to work with completely bounded maps on spaces of operators, unlike in the case where you have just bounded maps on such spaces. Right. theorem that characterizes these objects is an extension of the previous theorem that I mentioned of Haagerup, Grothendieck, Haagerup, Euler, and it goes like that. Your function is a Schur multiplier precisely when, again, it has factorization. It factorizes in the following way now. You take a representation of your sister algebra rho, so representation rho, star representation of your sister algebra, and you have, you take two functions. Now these functions will need to act in the right spaces, will be essentially bounded functions, weakly measurable in the correct setting, in the correct sense. They will need to be valued with specific, the target space should be the right one, so that you get what you need to get at the end. So suppose that rho acts on some Hilbert space K, then V of X should act from H into K, so that this multiplication here, this product makes sense. So that phi xy at A, remember that's the Seidel map, at element A of the sister algebra will be just equal to this composition here. So you act with rho on A, and then you multiply on the left with V of X, on the right with W of 1, W star of 1. Right. As I said, when your A is a scalar, this reduces to the already known result that I described above before. Now, this is the version of Schur multipliers. How about Herz-Schur multipliers? So what do you do in case you have a group and an action? So now you have a group G, a locally coupled group again, equipped with a left-hand measure. As before, I didn't mention that all my L2 and L1 spaces are with respect to Haagerup measure of the groups, a left-hand measure. You have an action of G on A, therefore you have a corresponding sister dynamical system, and associated with that is, of course, the cross product of this dynamical system. This is one way to define it. Well, that's the way to define it. Covariant you define covariant representations of your dynamical system. If you have, so these are concrete, sort of concretely designed covariant representation. Your algebra is concretely represented on the certain Hilbert space H, and then you design this sort of canonical pair of maps, which constitutes a covariant representation. It acts on L2 of G with values in H. The cross product is then just the completion of the image of the L1 algebra under the covariant representation. So you have an L1 function with values in A. You take this representation pi pointwise at f of s, multiply with a lambda s. Lambda is the canonical unitary here. Integrate. That's a generalization of what was the case when A is the scalars, as before. You close it, and that's the reduced cross product. Now, it has, as I said, an operator not inherited from being a subset, a subspace, a subalgebra of the bounded operators on L2 of G with values in H. How do you define then Herz-Schur multipliers? Let's concentrate just on this second bit of the slide here. I will talk about specific representation later on. So what we do is you take now a function f defined on G, but with values in the Seidel maps of A again. So if you're given an L1 function, remember the cross product is generated by the L1 functions, A-valued L1 functions on G. You can define another L1 function, capital F dot little f, at the point t. You take little f of t, which is an element of A, you act with capital F of t on this little f of t. This is another element of A. And then what are Herz-Schur multipliers? Well, that is precisely the maps F, which have the property that the corresponding map, the map that I just defined, is completely bounded. Therefore, it extends to the cross product. It's completely bounded on this cross product. Now, one can restrict attention to the bounded one that are not completely bounded necessarily. And Haagerup and Canniere have this characterization of the completely bounded ones in terms of the bounded. The price you need to pay for that is you need to product your group with another group. So I will not stop in describing precisely the results. So the point is we have a similar result here. The result is, even if you forget about A being arbitrary sister algebra, but concentrate on the scalars, it's quite interesting, actually, quite nice. Being bounded with respect to any gamma cross G for any gamma, for any group gamma, is the same as being completely bounded, but moreover it is the same as being bounded with respect to the group SU2 times G. This is because of the representations. So we have a similar result here. Now, what happens if you discrete to scalar valued? Well, remember in general we have functions that are operator valued, sister algebra valued. If your sister algebra says the sister algebra is unital, assume unitality, then you just can consider multiples of the unit of the sister algebra. So this is same as scalar valued functions. Not surprisingly, they are Herz-Schur multipliers precisely when they are Herz multipliers in the classical sense. So at least in this level, our definition agrees with what we expected to agree with. And now the version of this transverse results in varying one variables into two variables also holds true here in this setting. Of course, you need to take into account the action of G on A. So instead of just multiplying inside the argument T as inverse, here I will need to adjust it accordingly, taking into account the action. In any case, I can design another map now on two variables, a suitable map on two variables, associated canonically with the map on one variable that I started with, in such a way that I have a transference resulted before capital F being Herz-Schur multiplier, precisely when this two variable function being a Schur multiplier in the sense that I defined it before. Moreover, the Herz-Schur multipliers can be characterized within the space of all Schur multipliers. So now we can view them as a subspace of the space of all Schur multipliers. They can be characterized as the invariant part of the Schur multipliers. What do I mean by that? Well, along with the left regular representation, let me consider the right regular representation as well of G, again on L2 of G, and let me consider this twisted automorphism. Now, alpha of T was the automorphism of the sister algebra A that corresponds to the point T of the group. Here I tensor it with the conjugation by the right regular unitary rho T. It turns out that the Schur A multipliers, which are Herz-Schur A multipliers, are precisely the Schur multipliers that are invariant with respect to this section, meaning that the corresponding map SV commutes with each one of those for every choice of point T in the group. So again, Schur multipliers give rise to bounding mappings on the compact operator tensor with A. I'm singling out those which commute with another action there, namely this action, and what I get is precisely the Herz-Schur multipliers, the one that will leave the cross product invariant. Once your map leaves the cross product invariant, then necessarily it will be you can design this map on one variable. Given a map on two variables, you can design it then a map on one variable which will satisfy the property of Herz-Schur multipliers.
So everything is all the basic one's left regular, and this is the diagonal of the right regular with itself.
Indeed, yeah. Right. So special classes of multipliers. Yeah. So these maps are quite general. Well, quite general. I don't know how general, but they are general in the sense that they include subclasses various situations. So over here, I talk about this what we call convolution multipliers. So these are map arising from measures. So suppose now you have again a sister dynamical system, and you have a measure on the group G. I can associate with this measure a map on the sister algebra, defined like that here. So that's a completely bounded map on the sister algebra. And now, for every measure, if I have different measures from the different points of the group, I have a family of maps on the sister algebra. I can consider the corresponding function that takes a point to the corresponding map to mu t, where mu t is the measure corresponding to point t. And I can ask myself which one of those are a Herz-Schur multiplier. So this we call convolution multipliers. If you have only one measure and every other measure is equal to that measure, then you do have a convolution multiplier arising that way. In general, you may have something more. For example, start now with an abelian locally compact group with dual group gamma, let's say. And let me consider theta the left regular representation of the sister algebra of gamma, of the dual group, on L2 of gamma. Now, every point from the group G, of course, can be viewed as a function of gamma, here comparing duality. And therefore, I can consider the following map. So starting with the generator here, lambda gamma of f, so f is a function, L1 function of gamma. So that's a function defined that lives on gamma, defined on gamma. I can multiply it pointwise with the character s. I have another function. I can consider the map then sending the left regular represented f to the left regular represented sf. So this is an action on C star of gamma. If you want to consider the Fourier transform, this is just the action on C0 of G by translation of the corresponding point S. Just more convenient for me to consider it in this picture instead of the level of C0 of G. So the Fourier transform of C star of gamma is C0 of G by multiplication from L2 of G. The method I'm discussing here, this automorphism of the sister algebra of gamma, when viewed in the Fourier transform picture, is just the translation by point S. Now the space of all compactly supported functions on gamma cross G is dense in the cross product. C star gamma crossed with G. So the action here is this one. And therefore, I can consider two classes of multipliers. So one class of multipliers of virtual multipliers. One class is where I do not change f at all. So if little f is in L1 of G, I don't change it in any way. What I'm doing, I scalar multiplying by a function depending on u of t. So u of t is u is a function depending on variable from the group G, scalar variable. I'm just multiplying this generator of the cross product scalar wise, point wise with u of t. U of t is scalar. And on the other hand, I can have another class where I do not change t at all, but I multiply the function f by a function on gamma. Right. So here, what I'm doing is I'm taking my function f, multiplying it with v, and I'm considering the corresponding element of the cross product. So on every fiber lambda t, or on every fiber arising from the group G, what I'm changing there, I'm changing the corresponding coefficient coming from C star of gamma. While in the previous case, what I did is I'm acting on all the fibers, not changing the coefficient at all. Coefficients stay the same. I'm changing all fibers by a scalar multiple of these fibers. More generally, I can consider maps on two variables now, on gamma cross G, and I can multiply a function, the function f, which is just a function of gamma, with a slice of this function at the point t, and consider this transformation on the generators of the cross product. Let's have a more concrete look of those maps. So as I said, C star of gamma via Fourier transform is C0 of G. The action there is translation by the group, by the elements of the group. The cross product is the same as nothing else but the compact operators on L2 of G via the Stone-Von-Neumann theorem. So this cross product is just the compact operators on L2 of G. Which maps are those that I was talking about in this picture? So which are they precisely? Well, the one that depending only on the variable from the group G will be the map that corresponds to the Schur multiplier n of u. N of u in the classical set that I defined in the beginning. So given a function u from the Fourier-Stieltjes algebra of G, Fourier-Stieltjes algebra, now here we have a billion groups. The Fourier-Stieltjes algebra is just the Fourier transforms of the measures on the dual gamma. Take measures on gamma, take Fourier transform certain functions on G. This is called the Fourier-Stieltjes algebra. Taking an element of the Fourier-Stieltjes algebra, it is known that these are precisely the completely bounded Hertzsprung multipliers of L of G, in the case G is abelian. So therefore, via the Bureko-Fender theorem that I formulated, in the beginning, n of u, this ampliated function on two variables, will be a Schur multiplier. In other words, it will be some function on the compact operators on L2 of G, some operator acting there. The operator that I described on the previous slide, this one over here, when I view my cross product as the compact operators on L2 of G, is just the Schur multiplier corresponding to the function u. What about the other one? The other one that didn't change the fiber, the place of the fiber corresponding to t, but change the function aside, the coefficient. Well, now I start with a measure on G. So remember the measure. If I take the Fourier transform, I have an element of the Fourier Stieltjes algebra of gamma now. Starting with a measure on G, a regular real measure on G, I have corresponding maps on the compact operators on L2 of G, which is given by conjugation or by right unitary operators integrated against the measure mu. So this is the corresponding completely bounded maps. So these two classes of maps, in a sense, are dual to each other in some sense, and they commute with each other. And the convolution multipliers that I define here are extension of both of them. The extension, they are a larger class than the class that these two classes. The larger class than the algebras generated by these two classes. So a natural question here is you have these two classes of maps, they commute with each other, they are Seeber maps on P of L2 of G, or the compact operators on L2 of G equivalently. They commute with each other, they generate a certain algebra. Is it all? Does it exhaust all convolution multipliers that I defined before? So this we do not know. We know, however, that the algebra of all convolution Schur and Herz-Schur multipliers is maximal abelian. So if we prove that this algebra generated by these two classes of maps is not only abelian, which it is, but maximal abelian, then that would settle the question. Now, approximation properties. Let me spend the last 5 to 10 minutes, most I will finish a bit early, I think, on approximation properties. So this it's not related to the previous several slides at all. So now I'm going back to the situation where they just have a discrete group even in that case, and group G is called weakly amenable. If I can find a net of functions, scalar valued functions of G, finitely supported, each one of the elements of the net is finitely supported, it tends to 1, the constant function 1 pointwise, and the Herz-Schur norm of each one of those functions is 1. The supremum of those Herz-Schur norms is 1. Is finite. Now, a sister algebra, on the other hand, A, is said to have the completely bounded approximation property if one can find a net of completely bounded, moreover finite rank maps on A, which approximate the identity map on A pointwise, with the property that the CB norms of these maps are uniformly bounded. This is one of the approximation properties that was studied in the category of operator algebras. It has a counterpart for von Neumann algebras, where your maps will be, I don't have it here, your maps will be normal maps in addition to that. Convergence will be weak star convergence. And we know via the work of Haagerup that a group is weakly amenable precisely when the corresponding group sister algebra has the completely bounded approximation property, and precisely when the von Neumann algebra of G has the weak star version of the completely bounded approximation property. So weak amenability is related, for example, to other approximation properties. It is a weak and often relaxed version of nuclearity, for example. For nuclearity, again, you have approximation, finite dimensional approximations like that, but you insist that your maps be completely positive instead of completely bounded on. So there are various relaxations, in a sense, sister algebras that are not, or von Neumann algebras that are not as good as nuclear ones, but still not as bad as just anything. They still have some approximation properties. You can still do some finite dimensional approximations in there. Well, what happens if you have if you consider the corresponding notion for cross products, right? So this is the result of Haagerup is about group sister algebras, group fundamental algebras. How about cross products? So here is the result. So that's a result of my student alone now. The definition is not surprising to arrive at. Of course, that's the natural thing to do, I would say. You just have finitely supported now functions. Remember, they should have values in the completely bounded maps on A. Now you insist that there are also finite rank maps on A with the corresponding properties that at every point A you have convergence to the identity along the net, and at every point T of the group, and the corresponding Herz-Schur norm of this net. The corresponding Herz-Schur norms are uniformly bounded. So Andrew indeed showed that we have a version of Haagerup result in that case. He showed that the corresponding, so the dynamical system is weakly amenable in that sense, precisely when the cross product has the completely bounded approximation property. He has it, I think he has also the, I haven't included it here, but he does have also the Weak-Star version, the corresponding fundamental algebra cross product having the Weak-Star CDP here as well. Now, of course, this idea, I mean, this question of saying, okay, I mean, here is your cross product. When does it have approximation property? What does it mean for the group? What does it mean for the sister algebra? Of course, this is an old thing, an old idea, how to relate the property of the group and the sister algebra to the properties of the cross product. Certainly so. However, the contribution here is, I believe, the fact that the dynamical system is viewed as a one thing. You do not separate the group and the sister algebra. The results that he found in the literature before this were of a nature where he said, if the group is like this and the sister algebra is like this, then this is what happens, all conversely. So what he has done is characterizing this approximation property entirely only as a property of the dynamical system. And this was done in a sense, yeah, I mean, through consideration of these Herz-Schur multipliers that we developed previously with him and with Ludmila. Of course, I mean, there are quite a lot of questions that remain in that direction. There are a number of approximation properties that are of interest still. So I believe this is the beginning of some more observations, I believe, in that direction. And I will finish as I promised with earlier. Thank you very much for this.
Questions? Comments?
Can you put this back to the last slide to say something about the ideal structure of the
Perhaps. I don't know. That's an interesting question. Yeah. That's an interesting question. I don't know. Yeah. So what it will not catch surely is the ideal structure of A. But it will catch this maps Herz-Schur multipliers. They will catch possibly the ideal structure arising from the group G, combination of the group G. Because we have some class of ideals that's probably associated with coming from G alone, right? In the case of abelian groups, I guess you need to consider the Fourier transform of the set of functions that are zero somewhere on the dual group, right? That will give rise to some class of ideals in the cross product. I don't know much about it, but I'm sure that they have been around cross products. Maybe we can check later, yeah. But it will not, unfortunately. These Herz-Schur multipliers are maps that act on the fibers, right? So you fix a fiber corresponding to some element of the group, and then you do something on the sister algebra, on the coefficient there, right? And you do different things on the different coefficients, right? How you act on the coefficient depends on the point T of the group, right? But yeah, I don't think that it will detect ideal structure coming from A. Yes, 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 this is true. Yes.
Because these multipliers are really, they're like a
Yeah.
family of multipliers.
Yes.
Okay?
Yes, that is definitely true. Yes.
So that's a little, so it's impossible for a non-weakly immutable group to get a cross product at SCBAP, it seems, by this theorem, which is a little interesting.
I don't know. I believe what you asked. I believe it is true. Because once you have this approximating net on the level of CD maps domain, then you can. I guess maybe one should act with some function on those and obtain scalar value maps. The only question is with the boundness. Yeah, I'm not sure about the boundness of uniform boundness. So I have these maps which are with values.
Oh, I see.
This vector space here, CD of A, right? And I want to get scalar value maps. Very well. I mean, I can act with whatever. I mean, functionally, okay, fine. I get a scalar value thing, but I'm not sure about this property here.
Yeah,
I'm
so
not sure. I mean,
where I was confused. I was a little bit confused, but I'll talk to you later. I understand what you're saying.
So I mean, the scalar value case, or the weak amenability, will be all that you see here, just Fi being scalar valued instead of CD of A. I think I will take it back. I mean, to what I said, that I mean, I'm not so sure, you know, because of this problem here. I'm not sure that the nose will be.
Any more questions or comments? Thank the speaker again.
Thank you.
T and K in the main building.
So yeah.
I understand